All right, our next topic in Chem 132 is thermodynamics. And so we're going to shift gears a little bit and talk about something new. This is the first session in our discussion of thermodynamics about spontaneity and the three laws. You can connect this to OpenStax Chemistry section 16.1, and in this session we're going to talk about the difference between spontaneous and non-spontaneous processes and the laws of thermodynamics. Okay, so from your Chem 132 experience so far, you know that chemical reactions can be fast or slow. They can proceed all the way to the products or not. They can be affected by the temperature, and if gases are involved, then by the pressure and the volume of the container. And so we see that all of these reactions have these different underlying things going on, but is there something that connects why all of these chemical reactions are different? And the answer, kind of, at least, is thermodynamics. So you liberal arts students have studied your Greek and your Latin, and you know that thermo means heat, and dynamics means movement. So thermodynamics is the movement of heat, or in other words, the study of the interconversion of heat and energy. Thermodynamics will help us explain why chemical reactions go in the direction that they do, and to the extent how far to the products that they do. So we're going to start to unify these different things we've been talking about and explain a little bit about why. So a reaction that happens is one that we would call, in our chemistry words, spontaneous. So spontaneous has a chemistry meaning. How can we know if a reaction is spontaneous in the chemistry sense? So we say that a reaction is spontaneous if it occurs without any outside force or energy acting upon it. One way that you could connect this with things you knew before, if you could compare the K and the Q values for the reaction. If K is greater than Q, then the reaction is spontaneous. So it's going to proceed in the forward direction. Now, here we have listed Kp and Qp. That would work for Kc and Qc as well. And then we'll talk about that one of the ways is to use the equation delta G equals delta H minus T delta S, where G is free energy, H is enthalpy, T is temperature, and S is entropy. If delta G is less than 0 or negative, then the reaction is spontaneous. That's where we're going with this. So, using those ideas, which of these processes is spontaneous? You can choose all that apply. Okay, so a cold cup of coffee gradually getting warmer, that is not a spontaneous process. It is spontaneous, however, in the reverse direction, that a warm coffee gets colder. Iron reacting with oxygen to become rust, iron oxide. Yes, that is a spontaneous process. Without any additional energy input, that will happen. The smell of baking bread diffuses across a room. Yes, that is a spontaneous process. You cannot keep that delicious bread smell in. Precipitation of KCl from an unsaturated aqueous solution of KCl. So if it's unsaturated, that means that more KCl could go into solution, could be dissolved. So in that case, we're not going to precipitate in order to get to equilibrium. Okay, so we see that some of these processes are spontaneous and some of them are not spontaneous. We note that the ones that are not spontaneous are spontaneous in the reverse direction. So we said that the warm cup of coffee would get colder, and that we wouldn't get precipitation from an unsaturated solution, but instead we could add more solid, so we'd get anti-precipitation. That's a thing to think about. Another important feature here is that things like rust that are slow reactions can still be spontaneous. So spontaneous does not mean the same thing as instantaneous. It doesn't mean fast. It means that it proceeds in that direction to get to equilibrium. Okay, so why do reactions proceed in a particular direction? Well, one factor that you've talked about in Chem 131 is enthalpy. And maybe you remember that enthalpy is given the sign delta H, and it is the heat that is released or absorbed by a system under constant pressure during a chemical or physical process. Reactions are exothermic when the bonds in the product are weaker than the bonds in the reactants. So we make weaker bonds and release that extra energy. And reactions would then be endothermic, would gain energy when we have stronger bonds, so that that energy that's put into the molecules gets stored in the chemical bonds. So this reaction that's shown here is sucrose plus potassium chlorate produces CO2 and water and KCl, and we see that it is very, very exothermic. And in fact, if you take the sucrose in the form of a gummy bear and you add it to some potassium chlorate and heat it up a little bit to give it the activation energy to get started, then it will light the gummy bear on fire. I'll post a link to a YouTube version of that you can watch. It's kind of fun. Okay, so we said that enthalpy is one of the factors that helps us to understand things being spontaneous, but it's important here to note that spontaneous is not the same as exothermic. And so let's use some examples. For example, the combustion of methane, burning of methane, is exothermic and spontaneous. So once you get the fire started, you don't have to keep adding heat to it. It just goes. It's spontaneous. And it's exothermic, it's releasing heat. The next reaction is baking soda and vinegar to make the volcano, like you did in 4th grade. If you were to feel your volcano after it finished erupting, you would see that this reaction is endothermic. It absorbs heat, and yet it is still spontaneous. On the flip side, we have liquid water becoming solid water or ice. We see that process is actually exothermic, but as you know, it is not spontaneous above 0 degrees C. So at room temperature, it is not spontaneous, even though it is exothermic. So if being spontaneous and being exothermic aren't the same, then it must mean that there's something else going on. Okay, so to understand spontaneity, thermodynamics tells us that spontaneous reactions move toward lower enthalpy and higher entropy in general. We're going for lower enthalpy and higher entropy. And the rules for that game are the laws of thermodynamics. So the first law of thermodynamics is, don't talk about thermodynamics, is that in any process, the total energy of a system and its surroundings is constant. This is the conservation of energy law. The second law of thermodynamics, in any spontaneous process, the total entropy of a system and its surroundings always increases. We'll talk more about that one. And the third law of thermodynamics is that the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. We'll need some more explanation on that one too. Allen Ginsberg, the poet, has restated the laws of thermodynamics in this way that might help you. That the first law, because all energy and matter is conserved, is you can't win, you can only break even. The second law is that you can't even break even, because some of the energy will be lost to entropy. And the third law is that you can't quit the game, meaning that you can't get away from rules number 1 or 2 by going to low temperature, because the lowest temperature you can go to is absolute 0. Okay, so digging into these a little bit. The first law of thermodynamics tells us that the internal energy of an isolated system is constant. In other words, energy cannot be created or destroyed. It can only be moved around an isolated system. Now, if you imagine 2 bulbs like the ones we've got shown here, where you've got a bulb like the one on the left with the molecules all on one side, separated from the molecules on the other side. And if you opened up the stopcock between them, you know that the molecules would diffuse from one side to the other side until there were roughly equal numbers of molecules on both sides. Now, if we think about that in terms of the internal energy, we see that this system is not doing any work because the pressure on the one side where it's vacuum is 0, And so if work is negative P delta V equals 0, then we don't have any work. And it's okay if you don't really understand that. You should be able to understand also that because this system is isolated, because there's nothing sort of coming in or coming out, that no heat has been exchanged. So no heat has been transferred from between the system. So what that means is that there has been no change in the internal energy of the system. So that the change in internal energy alone does not account for why the gas expands. In other words, because the internal energy of an isolated system is constant, this helps us see that enthalpy is not the only factor. So enthalpy and internal energy are kind of related here. There must be another factor. That factor is entropy. So entropy, in addition to enthalpy, predicts the spontaneous direction of a chemical reaction or physical process. It can be a little bit hard to define entropy, but one definition I like is molecular randomness. Sometimes also talked about as chaos or disorder. Yet another way we might talk about it is how dispersed is the energy of a system, because spontaneous reactions move toward greater, more uniform dispersal of matter and energy. For example, here in this little figure at the bottom, you can see that if you have a hot object, object X, and a cold object, object Y, and if you put them together so that they can contact each other, we know that the heat will flow from one side to the other, cooling down side X and warming up side Y until they're the same. So what this tells us, when we get to the sort of end of this spontaneous process, we see that the energy, the heat energy, is dispersed over the whole system. And so the second law tells us that in any spontaneous process, the entropy of the universe increases. So the dispersal of the matter and energy in the whole universe increases. Enthalpy, internal energy, is conserved, can't create or destroy. Entropy is always increasing. Entropy is not what it used to be. And so what we mean by the universe is the sum total of whatever system we're interested in. So a system might be an object or a chemical reaction. And the surroundings, everything that is not that, is what a chemist or a physicist would call the universe. So if the entropy of the universe has to always be increasing, that means that in any spontaneous process, we have to increase either the entropy of the system or the surroundings, or both. We said that entropy is a state function, which means that it is not dependent on the path or the mechanism taken between 2 points. Like delta H, it only depends on the starting and ending points. We can't really measure entropy directly. There's no entropy meter. So we mostly talk about entropy changes. And just to define the sign a little bit, if delta S is positive, that means that the energy is more dispersed. And if it's negative, that means that the energy is less dispersed, which is the unfavorable direction. So the second law of thermodynamics states that entropy must increase in a spontaneous process. But some spontaneous reactions, like the one shown here, have negative values for delta S. How do you explain that? So remember, the second law says that delta S of the universe has to increase. And so even if delta S of the system goes down, it must mean that somehow the entropy of the surroundings is increasing enough to offset that. So the entropy of the system might decrease, but as long as the entropy of the surroundings increases enough to make the total entropy change positive, then the reaction is spontaneous. How do we know when delta S of the surroundings is going to be positive? We'll talk about that later. But so the key here is, remember, it needs to be both the system and the surroundings. This second law of thermodynamics leads to some interesting conclusions if you kind of, extrapolate a little bit. So according to the second law, the entropy of the universe will continue to increase until all energy and matter are uniformly dispersed throughout the universe. This is one proposal for how the universe will end, called the heat death of the universe. And it makes me think of a poem by T.S. Eliot that's really about the horrors of World War I. But the final lines are, "This is the way the world ends. This is the way the world ends. This is the way the world ends. Not with a bang, but a whimper." And so that makes me think about the heat death of the universe whenever the last chemical reaction happens and all of the matter and the energy are equally dispersed. It will just be a whimper as the universe goes out. Another expression of this is from one of my favorite comics, Toothpaste for Dinner. And so here it is. On weekends when your friends are all busy, On weekends when your friends are all social distancing and you don't have anything to do, here is a fun game to play. Stare at the wall and think about how eventually you and the wall both will be infinitely dispersed and at absolute zero in the heat death of the universe. And so I leave you with that, and we'll talk more about all these ideas next time.